So let me start by recalling the statement of the Lefschetz formula that we discussed last time. So we have a finite field of Q elements. We have a scheme which is always assumed to be of finite type and separated. And we have x k bar, which is just x times spectrum of the algebraic closure. And then, so here we have three operators, actually. We have the absolute Frobenius map. This is a morphism from this scheme to itself, which is identity on the underlying topological spaces and takes any function to its qth power. So we can decompose this write it as a product of the geometric Frobenius map, which is Frobenius here and the identity here, and another morphism pi, which is identity here and the Frobenius here, right? So, and then, well, we also have a map from xk bar to x. And if I start with a sheaf on x and say denote by f x k bar its pullback, then it has additional structure. Well, this additional structure can be, so this is a sheaf for here, but the additional structure, kind of the descent data, can be described in two different ways. Well, first of all, we have an isomorphism between pi inverse of this guy and f, right? xk bar. And that's just follows from the fact that composition of pi and projection is pi. So if you take any sheaf on x and pull it back, you get this property. But now, so let's take this and apply to both sides f inverse. Что? Что такое что? Пай. Это такое отображение из этой схемы сюда, которое здесь тождественно, а здесь Фробениус. Хорошо? То есть это называется еще арифметическим Фробениусом, это геометрическим, а это абсолютно. Okay? So if I apply this f inverse, I get an isomorphism between this guy and f inverse of f x k bar. So what is written here is absolute Frobenius applied to f xk bar, right? So, and last time we observed that this absolute Frobenius acts trivially on the tal side of any scheme in characteristic P. It takes any tal open set to itself, its identity. It's isomorphic as a functor on the étal side. It's isomorphic to the identity functor. And therefore, this, for any sheaf, this is canonically isomorphic to xk bar. So composing this isomorphism, we get an isomorphism between this sheaf and this sheaf. So this gives me a map. Well, this is an isomorphism, so I want to invert it and look at this map, which is inverse to the one that we constructed, and fx k bar. Okay? So vice versa, if you are given this isomorphism, then you can apply pi inverse to this and derive this. So these two structures, so a sheaf on xk bar with this structure is the same as the sheaf with this structure. This is called the Weyl structure. Weyl structure. So what we get from this is so we have a functor from sheaves on X to what I want to call Weyl sheaves. Well, that's not me. Sheaves on xk bar. So, and that is pairs consisting of f on xk bar with an isomorphism between its Frobenius pullback, the geometric Frobenius, and itself. Okay? So we have a sheaves on X, and we have sheaves here which are covariant with respect to this geometric Frobenius map. So the construction just takes the sheaf here and takes its pullback under the projection map. Okay? So, well, in fact, this functor is fully faithful, and it's almost an equivalence. So, well, given the Weyl sheaf is the same as I explained here, is given a sheaf together with this isomorphism. So if this map were a finite étal, then given a sheaf here, it would be the same as given a sheaf here with this equivariant structure, right? And this map is not finite étal. It's rather inverse limit of finite étal maps, because this is an infinite extension. So you can see the difference even in the case when X is spectrum of a field, say FQ. So what are sheaves on L-adic sheaves on spectrum of FQ? These are continuous representations of the group Z hat, right? And what are Weyl sheaves? So if X is point, then this is also point. So I just get a QL vector space together with this Frobenius, geometric Frobenius map. In the case when X is spectrum of Q, is just the identity map, right? Xk bar is K bar itself, and the only non-trivial, the only endomorphism of a point, which is K bar linear, is the identity. So Weyl sheaf on a point is just a vector space together with an endomorphism, right? Automorphism, sorry. So these guys are continuous representations of the group Z hat, and these are continuous representations of the group Z. Continuity means nothing. So, for example, you can consider representation of one-dimensional representation of z hat, where of z, where the generator 1 acts by multiplication by L, right? This is cannot be extended to a continuous representation of z hat. So more generally, so let's say the following. So QL local systems on a normal connected X is the same as continuous representations, finite dimensional continuous of the group pi 1 et al. X, right? And so let's recall the structure of this group. So pi 1 et al. Of X, well, first of all, this projection map gives me a map from the fundamental group of the algebraic closure, and this map, we know that this was an exercise in one of the first homework assignments, that this map is injective, and the quotient is a Galois group of k bar over k, which is the fundamental group of the point, right? And in our case, this is z hat. Now, if I call this projection psi, then Weyl's local systems, So Weyl's local system is by definition a local system here together with this equivariant structure. This category is equivalent to the category of continuous representations of psi inverse of z, right? So here you have a subgroup, let's say, and you can take its preimage. So this is a dense subgroup. Any representation, continuous representation of this group is determined by its restriction to this dense subgroup. But the inverse converse statement is not true. Okay? So this statement is obvious. Well, it's easy to prove. Well, first you reduce it to the case when x has a rational point, then you look at the fibers. So what do you have? On fiber, first of all, you have the action of the fundamental group of this guy. Together, you have this map, so which induces an extra automorphism of the fiber. So you have action of z, you have action of this group. So this gives you an action of the semi-direct product of this and this, which is precisely this, in the presence of plane. Okay? Good. So Weyl's is a mild generalization of just the category of sheaves on X. And now it's convenient for some geometric application. So Now, the theorem, which is this Lefschetz formula, the key result, is that for any Weyl sheaf on xk bar, so we are given x, we are given xk bar, so we have f together with this map from its Frobenius pullback to f, which is an isomorphism, and I also, I'll be using notation a little bit, I will call it f. We have the following formula. So this is sum over all points. I take rational points of x, and that's the same as taking k-bar points fixed under the Frobenius, which means that you take this scheme, you take the fixed locus, and you take k-bar points of that. And what you do, you take the trace for each point. So, well, if I have a point, k point of x, I will denote the corresponding point here by x bar. This is a geometric point. So I have the fiber of my sheaf at this geometric point. And this geometric point is stable under the Frobenius map. So this Weyl structure, right? So this structure, right? Remember that Frobenius inverse of, so in particular I have this, which is, so the map F induces a map on fibers, and this fiber is by definition f of x bar. So if my point is fixed under the Frobenius, then I actually get a map from a vector space to itself, and then I can take its trace. Okay? So this gives me. And so this is the left-hand side of the Lefschetz formula, and the right-hand side is, so there is a homological description of this, that sum of traces, well, -1 to the power I, of traces of the Frobenius map acting on homology of xk bar with coefficients in F with compact support. Okay? So again, this action here uses this Weyl structure. So, so this is, again, a mild generalization of this theorem that I stated last time. Last time we considered only sheaves on X, and now we can take any sheaf on a Weyl sheaf on xk bar. So the, it will, proof will, this generalization does not cost extra, so let's put it here. Okay, so that was the statement. Maybe one, there is another Ну, вы, значит, в случае нульмерных многообразий, это утверждение сводится к чему? Значит, ну да, но я не знаю, что тут сказать. Да. В случае нульмерных оно очевидно. Например, в случае постоянного пучка и конечного множества, что, собственно, утверждается, что количество неподвижных точек равняется следу эндоморфизма конечного множества, следу оператора f со звездочкой, который просто индуцирован автоморфизмом x на функциях на конечном множестве. Да, ну, so there is a, okay.
Я про формулу, которая говорит, что если множество неподвижных точек не изолировано, тогда сумма, сумма следов альтернирует, число Левшица, да, для пучка f равно числу Левшица, тоже альтернированная сумма следов ограничения пучка на множество неподвижных точек.
Нет, но, значит, эта теорема априори, ее можно было бы сформулировать, тоже мы в прошлый раз обсуждали, просто взяв любую схему над К-чертой и какой-нибудь ее эндоморфизм f, тогда, в принципе, по крайней мере, в случае конечного числа неподвижных точек, обе части имеют смысл. Но теорема не верна. Поэтому в такой общности даже в случае изолированных точек и произвольного не Фробениуса, а произвольного эндоморфизма теорема не верна. Здесь эта теорема, она, значит, здесь нет никаких предположений насчет x. X может быть, например, произвольно очень особым. И как бы даже в случае изолированных точек как бы сложно приписать кратности. То есть все равно верно, что правая часть равняется сумме локальных компонентов, но локальные компоненты более сложно строить. Вот. А уж что там делать? Ну, для неизолированных там тоже есть какие-то локальные компоненты в окрестности неподвижного локуса, но они еще сложнее строить. В общем, про это я не знаю. Вот. Okay, so here is another kind of cheap generalization of this. So here we considered QL sheaves. Instead, I could consider QL bar sheaves, or the same is true if we replace QL by any finite extension. So first of all, you can make sense of K sheaves, right? So you look at the ring of integers here, right? You consider, first you define sheaves or K sheaves. These are inverse system of sheaves over the quotient of this modular power of the maximal ideal, and then the same works. Okay? So, and by definition, a QL bar sheaf is the inductive limit of the category of K sheaves over all finite extensions. So, very good. Now, so I want to give a range first. So the plan of this lecture is the following. So first I will give a reinterpretation of this theorem in terms of A functions associated to a sheaf. And then I will explain a generalization of this theorem, which is to the relative case, where we have not just one x, but rather a morphism from x to y. And lastly, I will reduce the statement of the proof. Well, I will make the first step in the proof of the theorem. I will reduce it to the case when x is a curve, actually A1. So if time permits, I will also explain some applications of this theorem to geometric representation theory, namely to, I'll explain some character shifts. So good. So L functions. So L function is a generalization of zeta function of a variety. So let f be a QL sheaf on x, which is of finite type over fq. And then, so it's L function is the following gadget. So it's product over all closed points of x. For each closed point, you consider the following Euler factor. So that's going to be a polynomial in T. It's determinant of the following matrix. You take identity 1 minus Frobenius x inverse times T to the degree of x. And it acts on the fiber. So this is a polynomial. It starts with 1. So its inverse is a formal power series in T. So the whole, this is infinite product, makes sense as a element, as a formal power series in T. Right? I will explain this notation here. So what do I mean here? So I have a point x, which is a map from a finite extension of field k. That's its residue field. This is my x. And so if I have sheaf on x, I can pull it back and get a sheaf here. A sheaf here is the same as a vector space together with the representation of the Galois group of this field. So if you wish, I can do this and call this x bar. And so if I take a sheaf f and pull it back here, it acquires an action of the Galois group of this field over this. And this Galois group is Z hat and it has canonical generator called the Frobenius. Right? This is this Frobenius that stands here. So Frobenius is an element in Galois group of k of x bar over k of x. Which is, again, Z hat. OK, so does it make sense? Good. So now I claim that. So we have theorem. Let's give some names. So this is Lefschetz formula. And so here is Grothendieck interpretation of L functions. So so here is a formula for L function. Or maybe before I state the formula, let me sort of relate it to L functions. For example, we studied at this arithmetic geometry seminar. So for example, I can take, so what are QL sheaves? The most important example of a QL sheaf is a local system. So a local systems comes from a continuous representation of the fundamental group. Right? So this gives me F. And что? Да. Значит, мы рассматриваем вот этот слой. Значит, это просто по определению, это надо взять пучок на F и ограничить его сюда. На этом ограничении, на этом слое действует фундаментальная группа вот этого дела. То есть вот здесь действует, получается, векторное пространство с действием вот такой группы. В частности, действует вот этот оператор Фробениус, который есть образующий здесь. Значит, я беру у этого Фробениуса характеристический многочлен. Угу. То есть я пишу, вот у меня векторное пространство, вот у меня оператор. То, что здесь написано, это характеристический многочлен, ну, там, может быть, с точностью обратно. Ага, хорошо? Very good. So in this case, so we have F, and so we get local system. And if I have a point X, so I can think of this as, this gives me a map from spectrum of K of X to X. And in particular, it gives me an element. Well, it gives me a homomorphism on fundamental groups defined up to conjugation, because there are no base points here. And so here I have, this is Z hat, so here I have the Frobenius, explained there. So, and so if you have this representation now, you can look at the images of this Frobenius. This Frobenius gives you a conjugacy class in this fundamental group of X. And you evaluate, well, so you get a conjugacy class here, so you just take the trace. You take the character of this representation, evaluate it. Oh, so sorry, not the character. It's, I'd rather take the characteristic polynomial as opposed to character. So it's characters of powers of this element, right? So, of course, this is characteristic polynomial does not change if you replace a matrix by its conjugate. So you, so in this case, this you recover the notion of a function of a Galois representation of the fundamental group, the way it's defined in number theory. Mm-hmm. Okay? So now theorem 2, which is this Grothendieck interpretation, so is the following. So a function of x f t is equal to the product over all I of determinants of the Frobenius of the following characteristic polynomials: 1 minus Frobenius t, and now it acts on cohomology, ith cohomology with compact support of x k bar f x k bar. And so each determinant has to be taken -1 to the power I plus 1. Okay, does it make sense, Lisa? Okay. So I will explain how, well, sort of. I will explain how theorem 1 implies theorem 2. So, well, theorem 2 in particular implies that this function is rational, right, for any sheaf f. So this is a generalization of first Weyl conjecture, right? If f is a constant sheaf, then L is just the usual zeta function of a scheme over a finite field. Okay. Proof is uses да. Они взаимно обратны в сущности. Потому что на когомологиях... Что? На итальном сайте они взаимно обратны. Нет, теорема... ну, мы сейчас... ну я его... да, пучок. Да. Простите. Okay, so the idea is in the case of usual zeta function with sort of for constant f. So the idea is that if you take the logarithmic derivative, well, I recall that if you take the logarithmic derivative of usual zeta function, then you get the generating function for the number of points on a variety over a finite field. Да, вот сейчас мы ее будем доказывать. Но смысл, вот в частности, она значит, говорит, что она рациональная функция. Да, это произведение конечное, а то совершенно бесконечное. Хорошо? So, proof? Well, it's an exercise, in fact, on of mentor-Galois theory. So we'll use apply. So we want to show an equality of two power series with coefficients in the field of characteristic 0. The constant terms are 1, so it suffices to prove the equality after applying operator t, taking the logarithmic derivative, which is t dt log. So I will take this identity, I will apply this operator, and then Да, да, из теоремы 1 я выведу теорему 2. Что? Ну как, количество точек-то, замкнутых точек. Что такое замкнутые точки на схеме над конечным полем? Это вы берете точки над алгебраическим замыканием, а берете орбиты относительно группы ГУА. Это совершенно бесконечное множество. Ага. То есть рациональность совершенно не очевидна. Okay, so this is a very important trick in number theory and also in this context. So when you apply the logarithmic derivative, for example, to usual zeta function of a variety over finite field, you get what we denoted by nk t to the k, where nk is the number of points over a field over degree k extension, degree m extension of the base field. So that's what we are going to use here. So, okay, so I take the logarithmic derivative of A. Да. Okay, so I'm going to apply this. Да, Лиза. Да, да. Ага. Не, хорошо, что вы спрашиваете очень. Так, перебивайте дальше. Значит, so what I'm going to use, so we apply this, and we'll use the following result in linear algebra. So to say, so if you take the logarithmic derivative of the characteristic polynomial of an operator, of operator f acting on some vector space V, f is any operator, and I take the logarithmic derivative of its sort of characteristic polynomial. Then what you will get is sum over all n greater or equal than 1 of traces of powers of n acting on V times t to the. So does the statement make sense? По-моему, нет, потому что я продифференцировал. So how you prove it? You reduce it to the case when V is one-dimensional. You use, for example, Jordan normal form. And so in the case when F is one-dimensional, this is a power series expansion for this. Oh, well, many other ways to do it. Yeah. So anyway, so we're going to use this, and now let's see how it works. T d over dt of logarithm of L function x f t. Well, that's the following. So you take sum. Here I just formally apply this property. So the logarithmic derivative of the product is the sum. Now, because I have degree x there, so I'll need to put it here. And then I have sum over n greater trace of the Frobenius to the power negative n. Acting on the fiber. T to the n times degree of x. Right? So far, nothing happened. And now, so I want to relate closed points of x with k bar points of x. So if I have a k-bar point of x, which means a map from spec of k-bar to x, its image is a closed point. And this gives me a bijection between closed points of x and the Galois orbits in k-bar points of x. So if you have a closed point, it has a residue field. And in order to construct a k-bar point, you have to embed this residue field into a k-bar. And there are precisely this many ways of doing this. So I will rewrite this as follows. So this will be sum over d greater than 1. D is the degree. Now I take sum over points of fq bar. These are k-bar points. And x is a corresponding closed point. It's its image in x. So degree, degree of x is d, right? So x bar is a point here, and x is a corresponding Galois orbit. It's a closed point. And now, so what we'll have here, so trace of, now I take the geometric Frobenius, and I will use the fact that geometric Frobenius in the fiber is inverse to this arithmetic one. And here I will have trace of x bar and d acted upon x bar. Okay, so let's see what happens here. So every closed point of degree d gives rise to d geometric points, right? This Galois orbit consists of d elements. So so if you look at all geometric points which have the same image here, then these traces are actually equal because the representations are isomorphic, right? This fibers gets interchanged by the Galois group, right? So you have d equal terms here, and that's why you have this extra factor, and here I don't have the extra factor. So the other thing that I change here, I replace the arithmetic Frobenius by the inverse to the geometric Frobenius. Okay? And now, yeah, so I forgot to write t and d. That's what happened here. Now I want to look at the coefficient at, say, nth power of t. So this is a power series in t. Let's combine sum in n. Right. Thank you very much. Sum in n. Thank you. Ну, потому что у меня точка степени d, и поле вычетов-то, теперь мне как бы надо рассматривать, у меня базовое поле увеличилось. Да. Okay, thank you for, yeah. So, let's see. Yeah, so I erase this. So let's do one more manipulation. So I want to write it as this, and let's compute the coefficient. Yeah, maybe. So let's compute the coefficient. So I claim that this coefficient is equal to the sum over x in f q to the power m trace of the Frobenius to the power m acting on the same fiber. Okay? So look, so what contributes to this coefficient? So first of all, the contribution comes from points, geometric points, well, FQ bar points of x, which are defined over some finite extension whose degree d divides them. That's all I use here. That's the formula. Okay? So now, in this formula, you should recognize, now I want to use the Lefschetz formula, right? So I want to rewrite this as -1 sum over I of -1 to the power I, sum over all m, trace of the Frobenius to the power m acting on homology, ith homology with compact support of x k bar, all these coefficients in f, x k bar. And so that's, yeah, this is, let's see, so this is, I need to multiply it by t to the m. Okay? And that completes the proof. Because, so you once again use this formula and compare it with what we have here. Okay. Good. So here is an application. So it looks like L function is, well, is merely, well, this result about L functions is merely a reformulation of Lefschetz formula. So, and L function is, say, for local systems, it's just a way of writing character of representation. A character is determined by its values on this Frobenius, right, for points, because this Frobenius are dense among conjugacy classes by Chebotarev density theory. So, but surprisingly, L function is well, this way of writing the character as this product is very important because L function has some unexpected analytic properties. So, which sort of come from nowhere. So, so let's say an example. Let's take for x a curve, smooth curve. Smooth curve over k, not necessarily proper, and f irreducible local system. So what is a reducible local system? A local system is a representation of the tal fundamental group, continuous representation. And irreducibility means just that it's irreducible as a representation. Then L function. So what do we know about L functions of irreducible? Oh, sorry, irreducible. Right. I think it's okay. Yeah, it's okay. So so what do we know about L functions of irreducible local systems? Lisa, you explain this to us. There is a big conjecture, the most important conjecture. What does it say? Да, абсолютно. So the Artin's conjecture said that this is a holomorphic function on the entire complex plane. So Ft is a polynomial. So that's what it means for a rational function to be integral. Entire, sorry. So, okay, so let's see. What is L function? L function is equal to the product. So first you take trace of the 1 minus Frobenius on H0 with compact support. Take, H1. Yeah, and then you divide it by the trace, not the trace, the characteristic polynomial. Characteristic polynomial 1 minus F H0 and then determinant of 1 minus the Frobenius on H2 with compact support. So let's look at this formula, right? I just rewrote this Grothendieck interpretation. So this is a polynomial. So we would be done if we can show that this guy is equal to 1. That's what you want to show. So what is H0 with compact support of x k bar with coefficients in F? We did some computation last time. So first of all, without compact support, what would it be? X is not compact, any. Suppose so let's say first without compact support, just usual homology. What is the usual zero homology of a local system? Right. So this is let me call this right this vector space V, right? So I assume I want to express in terms of the representation. V is the fiber of my local system. So then this is nothing else but the fiber, the invariant elements, which is, well, pi 1 et al. Now of what? So what is the scheme I want to take the fundamental group of? This scheme, right? So this is x k bar. So, well, I claim that this is the usual homology. And the homology with compact support, well, is either equal to 0 if x is not proper, so, and this is obvious because you take some global sections which vanish at infinity, right? So, or this if x is proper. Okay? So now what is H2 with compact support? Well, we had Poincare duality last time. This is H2 H0, usually H0 of x k bar f dual, right? And then I have to dualize it. And we discussed it last time that this is coinvariance. Right? So now let's recall the structure of the fundamental group. So we have xk bar, we have pi 1 of x, and we have z hat. So I claim that if my representation is irreducible, then both invariance and coinvariance vanish. Let's show that invariance, this invariance vanish. Oh, okay, maybe I should have said that this is not, say, rank. Well, say rank of f is greater than 1. Otherwise, I could take trivial local system. Yeah? Yeah. So why it's true? Because if you take invariance, then on this invariance you have action of z hat. It's stable under z hat. So that means that this invariance would be subrepresentation. So if so, that means that this is a subrepresentation. So either this is the entire group, but then the action would factor through the abelian quotient z hat, which would force f to be one-dimensional. And similarly for coinvariance. Okay, that's good. So we proved Artin's conjecture. So let's maybe so this is 0, and this is also 0. Now, so let me explain a generalization of this theorem 1 in the relative situation, to the relative situation. And in fact, this generalization will be proved alone theorem 1. And this will be, that's how we will reduce theorem 1 to the case of curves. So, so let's see. In order to do this, so I want to explain for you Schiff's function correspondence. Which is the basis for the kind of very important in geometric representation theory. So, so suppose you have, so that's, I want to produce for you a map from isomorphism classes of Weyl sheaves on X to functions. Functions means just, well, no condition on these functions on finite sets. X, k. And these functions will be with QL coefficients or maybe QL bar coefficients. Well, you could replace, as I said, QL by any finite extension. So if you have F and you have the Weyl structure, which is this, ну, значит, что функции на этом множестве со значениями в этом... да, прости. Да, значит... okay. So if I have a Weyl sheaf, I assign to it the following function, and I will call it the characteristic function of F. And its value at point X is just the trace of the Frobenius, geometric Frobenius, on the fiber on this point. Very simple. So now, so suppose you have a map from X to Y. So in fact, a Weyl sheaf gives not only a function here, it gives function on all finite extensions of K, but they're not kind of compatible. So suppose you have now a map F from X to Y. Then it gives me a map from X K bar to Y K bar. And this map, that I will also call F, it's commutes with the Frobenius, geometric Frobenius, right? So this is F, and this is Y. So I have this commutative diagram. And so from this commutativity, I can use it to show that the inverse image of a Weyl sheaf on Y is a Weyl sheaf on X. So Weyl's sheaf. Oh, maybe I will write it here. So if I have Weyl sheaves on X, here I have Weyl sheaves on Y, And here I have the functor. I have two functors. So first of all, I have the inverse image, right? And using that f commutes with f, well, using that f commutes with the Frobenius, you see that a Weyl structure on a sheaf on Y gives you a Weyl structure on its inverse image, formally. Right? So shall I explain this? Okay. And there is also this functor. Let's say derived, well, this is the derived direct image with compact support. Well, I would say that I want to take the adjoint, but, well, so the adjoint are not exact. So you have these functors, and they also carry Weyl sheaves to Weyl sheaves. Now, here I have this map to functions. With values in QA. And functions on Y with values in QA. And here I also have two maps. So this is, well, if I have a function on Y, so x of k definitely maps to y of k, all right? Yeah, so that means that I can compose function. So this gives me this, the inverse, the pullback map. And if I have a function here, I can construct a function here. That's called the summation. So if you have a function, on x, and you want to apply it to, well, sigma of this function, evaluated at some point y, is just sum over all point x with f of x equal to y, chi of y. Right? And so a generalization of this theorem 1, which is kind of a relative version. Say again?
But it is some higher direct image. It's not to Weyl sheaf, but direct category.
Well, so at the moment, I want to avoid using derived categories. I just consider this Q. Well, I will formulate the statement. So you can define it in derived categories, but this requires some more technical work. And at the moment, I would rather avoid it. So an easy property is that if you start with a sheaf F, Weyl sheaf, you take its sheaf on Y, and you take its pullback, and then take the characteristic function, right? Apply that construction. Then this is the same as taking the characteristic function of f and applying f inverse to this. Right? This is trivial, just because the fiber of the pullback is the fiber of the f at the corresponding point. So this is tautologically true. But what is really non-trivial, theorem 3, is that so if you take characteristic function of f and then take sigma of that, right? Then you get sum over all I, -1 to the power I of characteristic functions of R I f chic of f. Okay? Does it make sense? So, in a sense, that's the kind of commutativity of this diagram up to this nuisance that here I have various q, and I would rather kind of define the sheaf function correspondence for the objects of the derived category as alternated sum on homology, and then this would be statement would be nicer. But again, this would require some more technical work. So, well, this is definitely if in the case when my y is point, right? The summation, this guy here, is precisely the left-hand side of the Lefschetz formula. And this is the right-hand side. So, so that means that theorem 3 implies theorem 1. But in fact, vice versa. So, and that is this formal consequence of base change. Recall that this functor satisfies the base change property for any morphism. The f low star satisfies only proper base change property. But this, we proved that, at least with finite coefficients, we proved that this has the fiber of this sheaf is compactly supported homology of the fiber. And this amounts to this property here. Okay. And now I will explain it's very short. Using somehow the idea, the construction that I explained here, how you reduce the theorem 1 to the case of curves. It'll take 2 minutes. So, so proof of theorem 1, well, I will do only step 1, reduction to curves. Okay, so first of all, a general observation. Suppose you have a short exact sequence of sheaves. Exact. If theorem 1 holds for 2 of this fi, then it holds for all fi, right? That's just because both sides are additive in short exact sequences. So, now, take any x and take dense open subset, dense affine open. So here I have the complement z, which is x minus u, and for any f, I have a short exact sequence. Jo star of f restricted to U. This is J. It maps here, and this maps to IO star of f restricted to Z. So if I know the statement here and here, I know the statement for f. So this Z has smaller dimension. So arguing by induction, I may assume that I know the theorem for Z. So it's enough to prove for this. Compactly supported homology of this sheaf is just compactly supported homology of f restricted to U. So that means that I may assume that x is affine, right? That x is equal to U. And now, in this case of affine x, I can use Noether normalization lemma to fiber it in curves. So I have x, f0 may be affine space. This is surjective. This is finite surjective. Finite surjective. This is a n minus 1. Just the projection. And finally, I have point. Right? This is f1. Now, so to prove, so theorem 1 for x will follow from theorem 3, the relative version, for each fi. Right? So I take the characteristic function of my sheaf here, and I'm interested in its pullback here, push forward here. So, but now the fibers are curves. And using the base change theorem, again, this implies theorem 3, 1 for fibers of fi. Well, the fibers of fi are either A1 or finite zero-dimensional schemes. I will leave you as an exercise to check that the theorem is true for zero-dimensional scheme. So conclusion is that enough to prove theorem 1 for x equal to A1. Okay. And that will be done next week.